This is a review for Unit D electrical principles. Um, First thing is that's important is the energy transfer and transformations. You have to understand that energy cannot be created or destroyed. It's just transferred from one form to another. And there are two main kinds of energies that we talked about. We talked about kinetic energy. We talked about potential energy. Kinetic energy is simply put is movement. So if something is moving, it has kinetic energy. Potential energy is an energy that is stored. So you could kind of think of it as something that has energy, but something that has the potential to do some work, so to speak. So an example of potential energy would be the food you eat. It's potential because the energy is stored in the chemical bonds. Another example of potential energy is if somebody holds a ball in the air and they're holding it up high, because it is a certain distance from the floor, it has potential energy, because when you let go of that ball, that potential energy will turn into kinetic energy. Now, mechanical energy is actually, technically speaking, it is the combined energy, a kinetic and potential energy of an object. There's also chemical energy, thermal energy, and electrical energy. They're all different types of either kinetic or potential energy. So chemical energy, as I said with the food example, is potential energy. Thermal energy is kinetic energy, because with thermal energy, it's the particles, as you gain thermal energy, particles move more and more. So that is kinetic energy. And electrical energy is a type of potential energy. It's the energy that's carried by charged particles. And I just spoke about the law of conservation of energy. So there are some examples here where energy is not created or destroyed, but just transferred from one form to another. So a good example is a thermocouple is a device that produces electricity from thermal energy. So the conversion is thermal energy to electrical energy. A cell or a battery produces electrical energy from chemical reactions. So it is converting chemical energy to electrical energy. And some other examples include a flashlight that converts the chemical energy inside the battery to electrical energy, and then that electrical energy is transferred to light. Of course, a lot of that energy is also lost as heat. So inefficiency comes into play as well. Energy is lost. So a blender is an example of taking electrical energy and converting it into kinetic energy. And a toaster is an example of taking electrical energy and converting it to thermal energy. An electric motor is something we talked about, and it can be a little confusing. An electrical motor is a device that's just used to turn something. It's going to convert electrical energy into mechanical energy, or electrical energy into kinetic energy. By winding current-carrying wire into a coil and wrapping it around an iron core, you can make an electromagnet. An electromagnet will move to line up with the magnetic field of a nearby permanent magnet. To keep the electromagnet spinning, the motors use something called the commutator. The commutator is right here, and all that is just a split ring. So it's a ring with, just split right in the middle. And there are some brushes attached to it as well. The commutator is split up because what it allows the commutator to do is that split breaks the connection of the coil. It changes the direction of the current. And if it's going to change the direction of the magnetic current, it's going to affect the magnetic force in the direction of the magnetic force. The armature will continue to spin because of its momentum. The commutator then reconnects, and that's how you get spinning motion. Okay, so that's an electric motor. There are two types of motors. There's a DC motor and an AC motor. A generator Again, two types of generators, just like two types of motors. There's a DC generator and an AC generator. Again, remember, DC stands for direct current and AC stands for alternating current. A generator is a device that produces electricity. It's going to convert mechanical energy to electrical energy. So it does the opposite of a motor. A generator works, as I said, like in the reverse compared to a motor. Instead of pumping an electric current into the armature and the armature turning as a result, you turn the armature and the current is generated as a result. So yeah, so direct current, alternating current, we talked about those. Transformer is important. It's a device that's going to change electricity at one voltage into electricity at a different voltage. There are two kinds. There's a step-up transformer and there is a step-down transformer. And we'll talk about those. Okay, we'll talk about step-down and step-up transformers pretty quickly here. So when a step-down transformer just means you're going from a high voltage to a low voltage. Okay, that's pretty intuitive. It also means that you're going from one side of the transformer where you have many coils and many turns to the other side of the transformer where you have few turns. Likewise, a step-up transformer is low to high voltage, and you go from an area with few turns to an area of the transformer with many turns. Step-down transformer, you go from low current to high current. Okay, so that's a little counterintuitive. And you go from in a step-up transformer, you go from an area of high current to the other side of the transformer, low current. Okay, static electricity. There are two kinds of electricity. We talked about static and current. Static electricity is the buildup of electric charges, meaning that the number of protons and the number of electrons are not going to be equal. Charged objects cause charge separation when they are brought close to neutral objects. For example, the buildup of charges in your hair when you put a wool sweater on, okay? Or when you walk across the carpet and you touch the light switch and you get a little bit of an electric discharge. There's a charge separation. These charges are transferred from the wool to your hair. For example, another example is lightning results from a buildup of charges in clouds. When the buildup becomes too large, the charges jump and they discharge to the ground. So just like when you're walking across a carpeted room, carpeted floor, and you touch something, that's the same as a lightning electrical discharge. So there are laws of static electricity. Like charges repel, so negative will repel negative, okay? And opposite charges, negative will repel negative, positive will repel positive, but opposite charges, okay, attract when it comes to electrical charges. A charged object will attract a neutral object due to charge separation in the neutral object. So a neutral object is made up of both positive and negative charges. So if you have an object that's charged and you're approaching a neutral object, that will attract a neutral object because the charges within the neutral object realign themselves so that the opposite charge, which is attracted, will go towards the side that is closest to the charged object that is approaching the neutral object, and the charges that are opposite that have an opposite charge of the charged object will just go away to the other side in the neutral object. That's kind of indicated here in this diagram. You can see that visually. So for example, in class, if we have, let's say we have got a teacher or a lab tech or whatever, and let's say it's a teacher. When the teacher rubs the balloon, rubs the balloon, here's the balloon here, took a balloon, rubbed it on his head, that negatively charges the balloon because the electrons from the hair move to the balloon and creates a negative charge on the balloon. When the balloon moves towards a neutrally charged wall, the wall's right here, so this is a wall, okay, the positive charges, the charge separation occurs. So what happens is the electrons move away from the negatively charged balloon, and the positive charges are close to the surface. So what happens is, because of these laws of static electricity, opposite charges attract. The balloon sticks to the wall. The second type of electricity we learned about is current electricity. And so current electricity usually starts at the negative pole, and it goes in the direction, it kind of just loops around. Okay, goes. This one has multiple pathways, so it would be a parallel circuit, as we learned, and it'll come back to that positive pole. So current electricity is the flow of electric charges. Okay, the more charges that flow per second, the higher the current. In general, electrical current carries electrical potential energy that's used to operate electrical devices. Again, this could be your iPhone, your laptop, your radio, whatever. So electrical energy carrying charges flow. Another example would be through a light bulb, where the electrical energy from the charges is converted to light and heat. So here we have batteries. Sorry, cells, not batteries. Actually, that's a good point. A cell is one source of electrical energy. Chemical energy is converted to electrical energy, and a battery is two or more cells together. So we have two kinds of cells here. We've got the dry cell here on your right, and we have the wet cell on the left. So let's talk about the dry cell first. Dry cell is a device that converts chemical energy to electrical energy, and they consist of two electrodes, and all electrodes are just two different pieces of metal and an electrolyte. That electrolyte in the dry cell is a conducting paste. So charges are going to leave the negative electrode, pass through the electrolyte, and return to the positive electrode. They're called dry cells because the electrolyte is in the form of a paste. A wet cell is the same thing as what we described here for a dry cell. However, the electrolyte solution is usually an acid. Okay, so this shows your two metals and the electrolyte here that allows charges to pass through them is an acid. Okay, and a common acid used for that is sulfuric acid you'd find in your car battery. Okay, there are two major circuits that we talked about, and circuits are just pathways. They allow paths. They are paths that allow electrons to flow. There are two kinds of circuits that we have here. Okay, the first circuit on the left here is a parallel circuit. So this is your parallel circuit. Parallel, and this one is a series circuit. Okay. We'll talk about the parallel first. Parallel circuit has more than one path. Okay. So current passes through each and every single load. So the advantage of this parallel circuit that is, if we break the current here, then it's not going to affect the functionality of the other bulbs. They'll still work. Adding a new pathway with an extra resistor will not affect the resistance in any of the other pathways, but adding more resistors in parallel will decrease the total resistance of the circuit. Okay. Just think about it this way: if you're drinking chocolate milk in a cup or glass, I should say, and you use two straws, it's easier to drink out of two straws than it is one because there's less resistance. The voltage is going to be the same throughout the circuit, so the voltage of the battery is equal to the voltage drop across each load. Okay, so voltage drop, again, we measure here across one load, across another load, and that's used by a voltmeter. Okay. As you increase the number of loads placed in parallel, the amount of current drawn from the energy decreases. Okay. The next circuit here is called a series circuit, and as you can see, the difference between the parallel and series circuit is in the series you just have one pathway for the electrons to flow. So if one load breaks in the circuit, the whole circuit won't work. So other bulbs won't turn off. If you increase the number of light bulbs, let's say, in this circuit, well, that's going to make the resistance increase. Okay, and if the resistance is going to increase with the increasing light bulbs, that's going to cause current to decrease, and that will cause the light bulbs to become dimmer as each new light bulb is added. Series circuits are used in households so that you can turn off all electricity in a circuit at once with a switch or a fuse. But in order to operate our devices, a lot of the circuits that are used in homes are parallel. Okay, so speaking of household circuits, I should say, there is a difference. You need to be able to compare, household circuits to microcircuits. And the main difference is the scale. Household circuits are larger. Electrical circuits are smaller. Household circuits have dozens of electrical components. On a typical microelectric or what's microelectronic circuit, there can be millions of transistors and resistors. Okay, so you're going to have more transistors and resistors on a microelectric circuit. So this slide here, I pulled some of these images from the internet. Well, all of them from the internet. This describes the relationship between resistance, voltage, and current in Ohm's law. So the equation for Ohm's law is the resistance is equal to the voltage divided by the current. Okay. So the voltage just has to do with potential difference. So a short waterfall, okay, is like just having one battery, right? The potential difference between this plus and this minus is not as great. So a short waterfall means that the distance from the top to the bottom is not as high as in a taller waterfall, so the energy is not going to be as much. Now, if we were to take a bunch of batteries and hook them up together in series, we would see that the potential difference, right, is much greater than in the shorter waterfall analogy. So that's like having, water falling from a much higher location. Okay, the current has to do with the amount of electrical flow. So here we have a lot of current here because we have lots of water falling, but it's a picture taken of the same waterfall where things are kind of, where there was a bit of a drought and there's like very little water flowing. So a wide waterfall, for example, has higher current. Okay, a wide waterfall is used to show or demonstrate high current. A more narrow waterfall will demonstrate or show low current. Okay, and resistance, I don't really have a picture here that shows resistance, but let's say if in this waterfall, well, actually not this waterfall, we'll have to draw two separate waterfalls that are the same height. So if I want to model resistance, I would increase the resistance by adding, let's say, a bunch of rocks here, right? If I had a bunch of rocks here and I have only a few rocks here, right, then this waterfall, okay, has less resistance than this one. So resistance is like driving on a road and having a lot of potholes, right? That's going to cause you to slow down, right? So just as this is going to cause water to slow down, or potholes are going to cause cars to slow down, resistance decreases the amount of current. Ohm's law, again, this is how they're going to represent the equation on the PAT on your final exam. But a good way to memorize Ohm's law is just by using the circle or this triangle. And if you cover up one variable, it'll show you how to get it. So if I cover up V, I can go I times R. If I cover up I know it's voltage divided by resistance. If I cover up the resistance, it's voltage divided by current. So here's a really, really quick example. And I love this example because it shows you exactly what you need to do to make sure that you get full marks. Now, on the final exam, you're not going to be marked on showing your work, but it is a very, very good habit to get into before you get into high school, because they're going to expect you to show your work and they will give you marks accordingly. Okay, so start with a variable stack. From your variable stack, you can work from there and you can just solve the problem. So this problem is solved for you, but it's a good example that a 10-volt battery is plugged into a circuit. If 2 amps of current run through it, how much resistance is there? So it's giving us our voltage and our current. We have to find the resistance. So we write our formula, do the substitution, and we find our answer. And do not forget your units. Okay, don't forget your units in the final answer. I would take this one step further and you can actually rewrite it and draw a box around it. But that's high school stuff. In PAT, you do the calculation and you'll see one of your answers as an option A, B, C, or D, or you'll have to fill in the numerical response. Power is another calculation. The power is the rate at which a device will convert energy. The symbol is P and the units are watts. So 1 watt is equal to 1 joule per second. There are 2 equations that describe the power relationships. Power is equal to the current times the voltage. Energy is equal to power times time. Here's an example. A toaster is connected to a 100-volt power source, and it has 5 amps of current flowing through it. How much power is dissipated as heat? Okay, so we take power is equal to I times V, 5 times 100. Power is equal to 500 watts. Now, this example doesn't show your variable stack, but it is something that is good for you to do just to kind of organize your calculations so that you will not make mistakes. Okay, here's another example. How much energy does a 100-watt light bulb consume if you leave it on for 2 hours when you're not in the room? Calculate the answer in joules and kilowatt hours. So again, sometimes you might have to think to yourself, man, when am I going to have to convert my time into seconds, or when am I going to leave it? All you need to do is just look at what they're asking you to answer your question in. If they're asking you to answer your question in kilowatt hours, okay, and let's say the time is given to you in hours, then you know you don't have to do any conversion. However, if they give you the information of time and let's say seconds, but they're asking for it in kilowatt hours, right, then you know you'd have to do a conversion. Okay, now when you're doing in joules, your time has to be in seconds. Okay, time has to be in seconds. Okay, time has to be that should be an S. Okay, so that means that time has to be in seconds. All right, so here's the example. Power is equal to 100 watts. My time is 2 hours. What's my energy? Well, because they're asking it for it in joules, we have to convert 2 hours into seconds. Okay, and you would take 2 hours, multiply that by 60 minutes for every hour, and multiply that further by 60 because you have 60 seconds in every minute, and you would get 7,200 seconds. So you calculate the energy. So you take your power, which is 100 watts, times it by 7,200 seconds, and you would get 720,000 joules. Of course, you would have to convert that to kilojoules, and so that means you would just go back 1, 2, 3, 720 kilojoules. Okay, so kilowatt hours is what we need to do. So for kilowatt hours, we have to take our power and multiply it by time. But look, it's in kilowatts. Okay, kilowatts, that's the key. So we got to take our watts and convert it to kilowatts, which is done here. Okay. If you have problems with conversions, I made another video on that. I've gotten feedback that it helps people. So go ahead and check that one out if you need to. So we have it in kilowatts, times it by 2, we have 0.2 kilowatt hours. Okay. Also, cost is something you need to do. Home stereo runs at 200 watts through a 120 volt outlet. If it is played for 3 hours per day and electricity costs 15 cents per kilowatt hour, how much does it cost to run the stereo for 10 days? Okay, so we have our variable stack. We have the power, which is 200 watts. Check. Voltage is 120 volts. Check. That's good. So time, we have 3 hours per day for 10 days. So that's important to know. And the cost is 15 cents per kilowatt hour. What's our cost for 10 days? This is a great variable stack because it anchors all the information, it summarizes all the information in this question. Okay, so now we're ready to do our calculations. Okay, so our kilowatt hours is power in kilowatts. Okay, so we got to convert that to kilowatts and times the number of hours. Okay, so take our power in kilowatts, which is 200 watts. That's 0.2 kilowatts times by the number of hours. Well, kilowatt hours. So that's 3 hours per day. So the good thing is we doesn't look like we have to do any conversion in terms of from seconds to hours because it's done for us. However, in this question, it's going to be on for 10 days. So to get our total time, we have to account for every single day. So we got to take 3 hours per day multiplied by 10 days. We get a total of 6 kilowatt hours. The cost is 15 cents per kilowatt hour. If we have 6 kilowatt hours, then it makes sense to take 6 kilowatt hours and multiply it by 15 cents per kilowatt hour for a total of 90 cents. So it'll cost you 90 cents to run your stereo for 3 hours a day for 10 days. Okay, so another calculation that you have to be able to do is efficiency. Efficiency is the output energy divided by the input energy. This example here asks you to kind of work backwards so that you can find out how much useful energy is produced when you have input of 200 joules of energy and it's a pulley system that operates with 40% efficiency. So after doing the calculation and necessary substitution, you find that the output energy is 80 joules. Okay, so everything's explained here for you on this slide. So the efficiency is equal to output divided by the input times 100. So you have to isolate the variable, right? So that's one way you can do it. So in order to isolate the output energy, you're going to have to isolate. So that isolating just means you just want it by itself on one side of the equation. So you take one side of the equation divided by 100. Whatever you do to one side, you must do to the other. So we have efficiency divided by 100 is equal to the output over the input. So output is not quite by itself. So because we're dividing input, to get rid of input on this side, we got to multiply it. So the input will cancel out, and whatever we do to one side, we must do to the other. So the output energy is going to be equal to the input times the efficiency divided by 100. So it's 200 joules times 40 divided by 100 gives you 80 joules. Okay. Alternative energy sources to electricity, or different ways of generating electricity. There are renewable and non-renewable resources. A renewable resource is a source of energy that can be replenished naturally in a relatively short period of time. Some examples of them are tides, water, which is just moving water that turns turbines that run generators. There are not a lot of tidal power stations in the world because it's difficulty in finding a suitable location. But they are considered environmentally friendly options. Another one is wind. So using the wind to turn a turbine that runs generators. Modern windmills, which looks like this right here, are more efficient than older ones because of the propeller. They are not particularly efficient, but they are environmentally friendly. They are usually grouped together, so you find a bunch of them together. Another one is indicated in this picture here is solar energy or sunlight. It uses the sun to generate electricity. So modern silicone materials have made sunlight more efficient way of producing current. This source of electricity is very environmentally friendly. Another one is biomass. So biomass is just biodegradable waste as it decomposes, produces combustible gases that are used for steam-driven generators. And this one here is a nuclear power plant. So heavy element atoms are split in a chain reaction, which produces energy that is used to drive steam-driven generators. And the last one is geothermal energy. Earth's heat will drive turbines attached to generators. So with renewable resources, there are also non-renewable resources. And a non-renewable resource is a source of energy that cannot be replenished naturally in a relatively short period of time. Alberta is very dependent on burning fossil fuels. So fossil fuels include coal, oil, natural gases. It's non-renewable source of energy, and it's not environmentally friendly. So burning fossil fuels is something that we depend on a lot, and there are some drawbacks to it. And one of the drawbacks is the environmental impact. So here are some things that will impact the environment. Burning fossil fuels produces something called fly ash. Fly ash is released into the air after you burn coal. And after you burn coal, the fly ash actually contains mercury, which is a poisonous metal that can damage the nervous system, as we saw in Unit C with the Minamata disease. Another problem with burning fossil fuels, or in industrial processes, is the production of sulfur dioxide. And sulfur dioxide, as we learned in Unit C, along with nitrogen oxides, produce acid rain. So carbon dioxide is a main greenhouse gas, and it causes global warming. Strip mining is a problem as well, and it's going to be is used when deposits are near the surface, and it removes all plants and animals from the area. So when you're strip mining, you're really disturbing an ecosystem, and you're upsetting natural habitats. And so animals, for example, have to find another place to live. Plants die off because they're removed. The natural environment after strip mining is never really fully restored. Oil and gas fire generators. Oil is burned to heat water, which becomes steam and turns a turbine to generate electricity. This process releases poisonous gases and warm water into nearby lakes and rivers. Okay. Alright, so there are issues related to energy. So we have shrinking natural resources because of high demand on natural resources to meet our needs, and environmental concerns as well. Sustainability is important for you to understand. It's a grade 7 topic that has been reinforced to you in grade 8, and again relearned in grade 9 and reinforced in grade 9. Sustainability is the whole idea that we have to use and manage our resources responsibly to make sure that people in the future of our society have access to resources. Okay, so we have to manage our resources. We have to improve efficiency of machines and appliances that we use. Whenever we have the possibility of using renewable resources to get our energy needs, we choose those over non-renewable resources. So it takes some personal decision making, and it also takes societal decision making. So these technologies that are based on electricity, like computers, cell phones, radios, etc., television sets are great. You know, they improve our quality of life. They make things more efficient for us. They're great. But there are some drawbacks. And one of the drawbacks, for example, with computers is, waste. Cell phones is waste, right? People typically renew their contracts every 2 years, and they get a new phone. Well, what happens to the old phone? Another drawback to electrically based technologies, especially with computers and cell phones, and the internet, is privacy, right? Um, Privacy is something that um, just is not as prevalent as it was in the past. Um, but technology using electricity has been great as well for other reasons. Medical applications, helping out with surgery, with dental work. It's been great for communication. Cell phones provide instant communication of words, pictures, voice, etc. And a person is almost always reachable. So if you need to get a hold of someone, you can. So that's the review of Unit D. I hope that was helpful, and we'll see you.